Good afternoon, everybody, and thank you, Chairman. I just firstly shout out to all of my colleagues around the country, doing it difficult in these times, particularly my colleagues in the eastern states, New South Wales, ACT and Victoria, who are certainly finding it quite challenging. And to those around the world, and hopefully we can get to see you all soon. I want to talk today a little bit about one of my favourite topics, and that's carbon neutrality in the construction sectors and how they relate to the development of standards. And just to start with a little bit of perspective, so when the federal government says that we're going to reduce our carbon emissions by 26 to 28% on 2005 levels by 2030, what that actually means is that a 50% reductions per capita and a 64% reductions in the emissions in the through the economy. So irrespective of whether the federal government wants to talk about carbon neutrality by 2050 or 60 or whatever as soon as possible, means every state government, every territory government has already committed to carbon neutrality by 2050. And there's a lot of conversations happening now, particularly around how do we make this happen, and very much from the government business enterprises such as roads and the like. I get often asked a little bit about vision for the faculty on climate change and on other things, but particularly to the topic today about what we see in the next 5 or 10 years. And I firmly are of the view that we have in place now today the pathway to get to carbon neutrality. And where we don't have the solutions, we've identified the research needed to actually deal with that. So when we talk about power to X, for example, you know, the battery side of how to battery storage, there's a lot of research going on at UNSW and around the country and indeed around the world on how this is achieved. So these things are clearly identified. The question comes about, what are we going to do about our side, the industry side of the economy? And we need big vision, and we need to address our share of what is a very important problem. It is just too important for us not to do this. And we talk about 3 ways. We know the pathways are either through dematerialization, using higher performance materials with significant efficiency gains, through substitution, taking a higher carbon product out and replacing it with a lower carbon one, or one that we don't talk about so much is on carbon capture, storage and reuse. But if we are going to deal with not just the cement industries, but other industries that also release carbon, I think this is an important part of the story that we do need to consider. Now, in 2015, for those who may remember, my student Yen Vu talked about their work in ultra-high performance concrete and their pathway forward to that. And they're working on developing substantial infrastructure without standards, using science and technologies, the way it was done 150 years ago before we had standardized methods and regulations. And these down here, we see here the bridges they're building. These are not trivial infrastructure. These are mainstream structure. And here on the top left here is how you demonstrate that through large scale testing. So there are standards being developed in France. There are standards being developed in Canada. An annex to their bridge code exists now, and they're developing the next generation of that. We do not have anything of that like in Australia. And the question then, is it chicken or egg? Do we not have a high strength concrete, ultra high performance concrete industry because we don't have a standard and we can't find a way of regulating through it, or because we don't have enough experience in building these to develop a standard. And this is really important because standards can be a real blockage, a real roadblock in the way of moving from innovation and innovative product development into implementation. I was quite privileged a few years ago to work with Howard Titus, Mario Tabone and John Biondo with Boral on their product for Aspire. At that time, 120 megapascal concrete, high stiffness, high replacement of cement, but a standard that didn't allow for anything above 100 megapascals. And in the end of this, question came into the committee, why are we restricting the standard to 120 megapascals? That was in the public comment, it should be 120. And the committee said, looked at it closely and said, well, sure, but what don't we know? So we don't have data on shrinkage, for example. We don't have data on creep, elastic modulus and things like this. But these are things that are all measurable in standard ways. So we don't need to have that solved to get community data to put into the standard on these. We can actually measure them. Then what can we use? What do we know well? So our models based on fundamental physical principles, design for columns, for example, we know the basic fundamentals of that, and therefore we can have high confidence in the way that we deal with these issues. And it got put in. And then in 2020, the amendment, some of the additional information about creep and shrinkage got added at that time. Cleaning up the industrial carbon is a challenge though. And we talk about cement production, and we know, of course, the process of changing calcium carbonate through to lime and then the release of carbon dioxide to the atmosphere. But it's not just our industries that have this. We look, for example, at silica production. Now, silica production is so important to the photovoltaics industries. It's the basis of most 85, 90% of the way solar cells are built. Coming out of technologies, out of Australian technology, out of UNSW, and it's penetrated the world. It's revolutionising the way that energy is done. You don't have to look around the houses in each of our suburbs to see how much uptake, local uptake of this has been. But silica, the production of that is actually very carbon intensive. In fact, 1 tonne of silica, depending on the purity you want to get to, produces 2.5 to 5 times the amount of carbon dioxide. That's 5 tonnes of carbon dioxide for every 1 tonne of silica. All right, so in the photovoltaics, we get the benefit back over time. But what about other areas, such as, for example, silicon chips? We can't work without silicon chips. I can't drive my car these days without the computer on board managing how the engine works. These are so fundamental. So if we're going to deal with this and other processes that release carbon to the atmosphere, we either say, okay, well, we'll clean it up through soil carbon or through plantations or other ways, or we do things like carbon capture and storage. And there is a nervousness about carbon capture and storage because it's seen by many as a way of perhaps extending the life of the fossil fuel industries. And that may very well be, but I don't see how you deal with cleaning up industrialized carbon without something like carbon capture and storage. And we see already in Norway, the Brevik projects that are coming on board, high volume carbon capture and storage for the cement industries, using the technology, using the spaces made available in the oil industries. In Queensland, Glencore's project, again, demonstrating the feasibility of carbon capture and storage. So these technologies are not new. They've been discussed for a long period of time. But to me, they are an important part of a bigger solution to cleaning up industrialised carbon. I want to give 2 examples in the time I've got left. One where we talk about substitution, one where we talk about high performance materials. So in substitution, we've been doing a lot of work over the last years through the CRC for low carbon living, and the strong support that we got, particularly from the ASA and the Australian Australasian Slag Association and the Fly Ash Association as well in this project. And we're looking at the ways of getting some demonstration projects out and acknowledge the work there, the large scale work of Wagner's, and showing that this technology works at scale. So we were looking at particularly a project here in a pavement trial. We wanted to look at whether geopolymer concrete was a substitution for pavements, because pavements take up very much of the concrete product. And this is where it is. It's in Wyndham Street in Sydney. For those who don't know Sydney, you see here the city of Sydney here, Sydney Airport. Wyndham Street lies just here. It's in an area, and if you know Sydney and Sydney traffic, and everyone trying to get to the airport at 8 o'clock on Monday morning, you'll know that every road heading between the two is extremely busy. So it's a very high traffic area. It might not look it, but it is. And this is the areas down on here. And we put in place 30 metres of pavement, 3 metres wide, 1 lane wide, and half of that was geopolymer concrete, and the other half was in conventional concrete. And here's a very young James Aldred sitting there testing the concrete using the rebound hammer. We had a quite challenging project because the road could only be closed Saturday morning at 7 a.m. because you can't wake up the neighbours before 7, so you can't start earlier. And the road had to be open at 5 a.m. the following Monday morning. So we had 36 hours after the completion of the casting of the concrete for it to harden to get to a sufficient strength to open the road. And you see also here on the right side there, the broom finish that was required for that particular project. We left there is the casting of the conventional concrete. This is the geopolymer concrete there, so heavy traffic fairly early. In fact, even though the pavement's 15 metres, it's the 13 metres that we're really monitoring. We actually ran out of concrete in the last geopolymer concrete, and because the trucks came from Brisbane, wasn't that we just go back to the yard and get some more. So this end part here is really the end of the truck. So about 13 metres we're monitoring here. And you can see the rebound helmet tests. So after 36 hours, we've got about 22 megapascals of strength. And at 597 days, 600 days, we've got about 45. So it's still performing, it's still hard. There's no indications of where along wheel lines, in either pavement, both are performing quite to expectations. On the left here is the geopolymer concrete. You can see here the 7th of April. You can see there the little ridges which are coming in from the broom finish. And of course, they've all gone. They actually went within the first year, as did in the conventional concrete. So I question what the point of doing that work on the broom finish was. But both performing similarly, both are performing well. And as I said, there's no real indications of any significant wear and tear on this at this time. On the issue of cracking, we've got one crack in the geopolymer concrete. It's actually a flexural crack. I suspect there's some subsidence issues with the way the sub base was doing. Not dissimilar in the ordinary Portland cement concrete slab. Again, it's a bit more shrinkage crackings in this, but nothing concerning. Everything as you would expect it to be. And again, a little bit of a flexural crack happening at one stage there. But again, and here's the cracks showing on the resolution on the left, on the right there. It's performing pretty much as you would expect it to be. And we'll continue monitoring that for 5 years or so. The next period will be April next year. Now, in the second project I want to just talk a little bit about is that of high strength steel reinforcement. And this is a project where InfraBuild funded a linkage grant to do some testing on high-strength concrete columns. And I remember Graham McGregor coming to my office and showing me this steel that they'd been able to develop, high strength, more than 800 megapascals, and it was bent around the size of a 20-cent piece. So very high ductility product as well as strong. And then the question is, well, where can it be best used? Where can the performance of these high strength materials be used? And columns is one area. The question is, well, have we maximized yet? We started that work only about 5 years, probably one of the shortest period of times from when the work started, got it into a standard. But the question is, have we actually maximized the benefit from that reinforcement? That's something I'll talk about in a minute. Tie reinforcement, shear reinforcement's an area I think we really need to look at as well, because essentially if we can increase from 500 megapascals to 750 megapascals, we can use a third less material. Right. So we tested 39 columns of different sizes and different reinforcement arrangements. The concrete strength is here, it's about 110 megapascals. The reinforcing steels, as you see, it's 520 megapascals for longitudinal steel is conventional. And then a 650 grade material, all tie steel was 810 megapascals, so it was of a high strength a high strength steel. So let's look at some of the results of this. So this is just showing the testing arrangements. You can see the loads applied at different eccentricities. We get the eccentricities approximately at setup, but we measure these strains both in the concrete through LVDTs, in the reinforcing steel through electronic strain gauges, and in that initial elastic period we can determine with high precision what the actual eccentricity is, so we correct for that. The one on the right here is actually a very ductile section. The I10 here, a value of 1 is something that's perfectly brittle, a value of 10 is something that's perfectly ductile, and this one here you see is very highly ductile. Anything over 5.6 is what we're looking at for AS3600. All right, so let's have a look at the results now. And I've plotted here two curves. The solid line here, perhaps look at this bottom left one, a bit more clear. The solid bottom line here, that's the model with AS3600. And the dotted line there is ACI 318. Now, it appears that ACI 318 is a better predictor. Problem is ACI 318 is a poor foundational model for high strength concrete. It was developed for members of 40 megapascal concrete. It was never changed. And you see in many circumstances, so these little green dots here, the green dots are for a 520 megapascal longitudinal steel, so conventional strength longitudinal steel. It's actually, the ACI model is quite a poor predictor. It actually overestimates the strength, even though it underestimates or gets the strength about right for the high strength steel. So the high strength steels here are the blue triangles on this specimen, and the green squares on that specimen. So we can see here, we're not capturing with great accuracy the test results. We're leaving a certain amount in the cupboard, if you like. We're not getting as much out as we can or should be doing. So let's have a look at that a little bit more detail. So one of the important parameters that we need to think about is the strain in the extreme compression fibre. So in AS3600, you'll know that we use a value of 0.003 for beams that are in bending. And then, of course, depending on what the gradient is, the steel, which may be 60 or 70 millimeters below the surface, will be something less, 0.0025, 0026, a value of less than 003. Now, 0025 is the strain for a 500 grade steel. So we're not getting any additional strength in that compression reinforcement because the model is dictating a strain at the extreme compression fibre of 003. And 003 is not a bad lower bound predictor, but it's a fairly poor mean predictor. And if we look at everything and we always err on the conservative, those conservative errors add up and we end up with a conservative model. The Canadians look at means and then they make the adjustments at the reliability level. And that's the approach which is much more sensible. And they have a strain of 0.0035. And if you look at 0035, it's a much better value of the average. And if we make just that change, nothing else, to the standard, we see that we get an increase, we get an improvement of not an inconsiderable amount. It reflects the data better and gives us less conservatism in our designs. And this is something I think we should strongly consider for future developments of standards to make sure that we actually get the most that we can out of our materials. Then the question is, can we go further than that? The way we do design is this traditional way here, or the way we deal with columns is we put this alpha factor here, and that is the point of when the cover spalls away from the column, and we basically lose the section. Let's take the core and let's think about what's happening to that. And if I can find the core sufficiently, I know two things. I'll increase its strength, but more importantly, I will increase its strain at peak strength. Now, it might increase the strength only by a few percent, but it increases strain considerably. Now, I'm not going to go through into these models. That's not so important. But let's say that we developed a model for the core and a model for our traditional column, and we simply looked at the maximum of those two conditions. And we look over here on the right and note that we're required to use 1% steel, 1% confinement reinforcement, irrespective with high strength concrete columns. And we see here anything that's less than about 450 millimeters square, we don't get any benefit. So our lab concrete, we don't see the benefit there because our columns are not of sufficient size. But if our column was a metre square in a large building, we actually get a 15% benefit. Then if we increase the core capacity from 1% to 2%, that goes up to 20%. How do we get empirical evidence of this? And that's the challenge, because these types of tests can be done, but they are not cheap. All right. So I just want to conclude here very quickly. Standardization continues on next generation materials and products. I think one of the problems, though, is the delay. 15 years to get something to standards is too long. Even if today we agreed, fully agreed, committee agreed, voted, it could take 3 years for it to get into the NCC and called up. So these things are far too slow. We need to be far more adaptive than that. So we need to increase the pace of standards development if we want to be responsive to change. And then finally, we need to also provide significant commitment and investment to research into low carbon industries and products, into how do we do big things? How do we test a column that's 600 mils square? We need governments, we need industry, we need the researchers to define the issues, and then we need to find the funding to do it, because the rewards can be substantive, but it can't be done without a whole of group, a whole of government, industry and research investment. So, Mr. Chair, thank you very much, and I will thank you and now pass it back to you. Thank you.